Hello, welcome back to Algebra. The title of this lesson is the distance formula, the midpoint formula, and the Pythagorean theorem. This is part one. We have several parts to these lessons. So as you can see from the title, we're going to cover a lot of material in one lesson. Now, most of you, probably everyone watching this lesson, has had some exposure to the Pythagorean theorem before. You've also probably had some exposure to the distance formula before, and some may or may not have had some exposure to the midpoint formula. What we're going to do is first we're going to review and talk about what that Pythagorean theorem is, why it's important. And then we're going to show you that the distance formula that we use in algebra and that we're going to learn in this lesson is basically a direct extension. It comes from the Pythagorean theorem. So it's almost like they're the same exact thing, and I'm going to show you that. A lot of times students don't understand that the distance formula is just nothing more than what they already understand in the Pythagorean theorem. We'll also talk about this midpoint formula. So we're getting kind of into coordinate algebra, coordinate geometry. There's a little bit of overlap between what we're learning now and what we've learned in geometry in the past. But we're going to go a level deeper because we're into the more kind of advanced algebra here. We're going to go a little bit deeper. I'm going to also take the opportunity to show you why this stuff is so important to modern science and math. I want you to understand that the things that you're learning are not just useless things. They're extremely important even to modern science, modern physics, modern chemistry, modern engineering. And so I'm going to get into it as we get into the lesson a little bit more, but just as a kind of an advanced preview, right? This concept of the distance formula that we're going to learn here, it really only, as we're going to learn it in this lesson, it applies to when we draw pictures on a flat sheet of paper or when we draw pictures on a flat board like this. We can calculate the distance between any 2 points. That's what the distance formula does, right? If you've studied it in the past, you know that that's what it does. In other words, I can put 2 points on the board and I can figure out how many centimeters are between those 2 points if I set up a coordinate grid and go from there. Now, in 1915, someone you probably heard of, Albert Einstein, proved what we call now the general theory of relativity. It's Einstein's theory of gravity, right? So you might think, why are we talking about gravity in an algebra lesson? It's because when you really dig into the details of relativity theory, which is one of the crowning achievements of modern physics, right? The understanding of gravity not being a force between things, but gravity being the curvature of space and time. You probably heard that, curvature of space and time, curvature of what we call space-time. When you drill down into that theory, into the nitty-gritty details in advanced physics, what you're going to find out is the way that you measure distances in space-time is very similar to this distance formula that you're going to be reviewing in this lesson right now. So we're going to be covering how to calculate distances between things, but just keep in the back of your mind, something that you think is simple like this is something that Einstein worked on for many, many years to prove that when space and time are curved, which you can measure by using this distance formula, that gives rise to what we actually call gravity here. And I know that that's beyond the scope of an algebra class, but that's something I want to point out because it shows you that the things that you're learning now have real uses for real science and advanced physics and chemistry and engineering. So let's dive into it. We're going to recall something before we get into the distance formula. We're going to talk about and review something we call the Pythagorean theorem. Pythagorean theorem. And I'm going to spend obviously time talking about the Pythagorean theorem and the distance formula and all that, and then I'm going to show you a little bit more about this curving of space and time just because I want you to understand generally how this stuff is used in more advanced concepts. So it all has to do with triangles. This Pythagorean theorem has to do with triangles, right? So when you learn it, you learn about the concept of what we call a right triangle. A right triangle is a triangle, any triangle that has one special property, and that is that one of the angles is 90 degrees. So that means that this is a 90-degree angle. 90-degree angle means it goes straight perpendicular like this. So 90 degrees is exactly like a straight L. There's no opening up of an angle. It's straight down on top of perpendicular to the line under it. So that's a 90-degree angle right here. Now, when you have a triangle like this, you have side number 1, side number 2, side number 3. We generally call them side A, side B, and side C. And side C here has to generally be the longest side. So we kind of label the longest side being C. A and B, it doesn't really matter what we call it, but we always want to use the variable C to represent the longest side of the triangle. We also call this the hypotenuse of the triangle. I know that you've probably learned that when you studied geometry, years ago. All right, so the Pythagorean theorem basically says that if you have a right triangle, it has to be a right triangle with a 90-degree angle. And if the longest side is labeled C, then it says that the square of that side is equal to the square of the other side plus the square of the third side. So c squared is equal to a squared plus b squared. One of the most famous formulas. I know you've probably seen it. If you haven't seen it, that's okay too. We're going to go from the very basics here. But you might look at this and say, what does this mean, right? What it means is that if I take a right triangle, as long as I have a 90-degree angle here, if I measure this to be 23 centimeters, and I measure this to be some other number of centimeters, and this to be some other number of centimeters. If I square the length of this side, and I square the length of this side, and I add them together, it should always be equal to the longest side squared. Now you might look at that and say, how is that true? How do you know that's true? Well, it's kind of like, how do I know I have 5 fingers on my hand? Well, I count them, 1, 2, 3, 4, 5, I have 5. You don't really prove, how do I know I have 5 fingers? You look at it and you say, I have 5 fingers. How do I know I have 10 toes? On both feet. Well, I count them. I have 10 total, right? It's an observation. How do we know this is true? It's because if I take a ruler and measure this line and measure this line and measure this line and plug it into this equation, it actually always equals. No matter if the triangle is really big or really, really small, as long as there's a 90-degree angle in there, the longest side squared is going to be equal to the other 2 sides squared added together. That's called the Pythagorean theorem. It holds for all triangles. But here's the big catch, right? And we're going to do a couple of examples here just to show you, but this Pythagorean theorem is only true when you draw the triangle on a flat space. We call it a flat space, which means this board is flat, right? So we draw the triangle on a flat space like this, then it of course all works in that Pythagorean theorem. If, in contrast, and I know this is not a great globe, but it's a little sphere, if instead I draw those points of the triangle on a curved surface. So Einstein talked about curved space and time. So this is a representation of curved space time, right? If I draw one point of the triangle, another point of the triangle, another point of the triangle, and I verify it is a right triangle, same as this, it's just I'm drawing it on a curved space. If I take one side squared, the other side squared, and then add them together and then compare it to the longest side squared, then it will not be equal like this, because this Pythagorean theorem only holds in a flat space. It doesn't hold when the thing is curved, when you draw the triangle on a curved thing. So you say, why is he telling me this? Why do I care about that? I'm just pointing out that that's a use, a very, very famous use of a very important result. Because when you have space and time that are curved, which was what we call gravity, that's what we call the thing that holds us to the ground, that curvature of space and time can be measured by how much it doesn't really work in this equation. In other words, this equation works for a flat triangle, but if it's very slightly curved space, then it'll be almost equal. If it's really, really curved, like a black hole, then this inequality will be really far off. The c squared will be totally different than a squared plus b. So the more curvature you have, the farther away from the Pythagorean theorem, the farther away it doesn't hold anymore, right? The flatter the space, like this chalkboard or this marker board here, it holds exactly. Right? So keep that in the back of your mind as a use, a very famous, important use in more advanced math and science down the road. But for now, let's get back down to reality. Let's take a look at our triangles. And of course, this is in a flat space, right? So let's say I have a triangle with 3 centimeters this direction, 4 centimeters this direction, and 5 centimeters this direction. Is this a right triangle? Well, let's check it out. We're going to say that A is equal to 3, and B is equal to 4, and C, which is the longest side, remember, is going to be equal to 5. And we're going to check that out. We're going to say, well, is c squared equal to a squared plus b squared? Okay, well, we put c in here. We say, well, 5 squared's on that side. 3 squared goes here. And then 4 squared goes here. And we're asking ourselves, is it actually equal like this? Well, 5 squared is 25 equals question mark. 3 times 3 is 9. And then 4 times 4 is 16. So then what I have is 25 equals, this when you add it up is equal to 25. So because you can look at this triangle and say a distance of 3, a distance of 4, a distance of 5 works exactly equally in the Pythagorean theorem, then you can say with certainty that this has an actual 90-degree angle here. Yes, this is a right triangle. It's a right triangle. All right, now let's take another triangle. We'll kind of make room over here. Let's take another triangle and see how it compares. Let's take another triangle. Let's say we have a triangle that's really long and slender like this. Let's say this has a distance of 1 centimeter, a distance of 9 centimeters, and a distance of 11 centimeters. And we want to ask ourselves, is this also a right triangle? Well, in this case, A would be 1, B would be 9. We don't care labeling A and B these sides, but we care that the longest side, C, is always labeled with the longest side, so C is equal to 11. So again, we'll say C squared is A squared plus B squared. We'll ask the question anyway. C squared is going to be 11 squared. We'll ask ourselves, is that equal to 1 squared plus 9 squared? Well, 11 times 11 is 121 when you stick that in your calculator. And 1 times 1 is 1, and 9 times 9 is 81. So you can see the right-hand side is going to be 82, and the left-hand side is 121, so that's not equal. So because you put these lengths into the Pythagorean theorem and it didn't work out, they're not equal, then what you have learned from this is not a 90-degree angle. I've drawn it close to a 90-degree angle because I'm sketching it, but if you actually measured 1 and 9 and connected it with 11, then you would find out that this angle is very far away from 90 degrees. Now, bringing it back to modern thinking on science, okay, we looked at this first triangle. We said this one fits with the Pythagorean theorem. Why? Because 3 squared plus 4 squared is equal to 25, which is the longest side squared. What I was telling you before is that this relation of the Pythagorean theorem, it only holds when you draw things in flat space-time, flat space, right? If I were to take that globe that I just showed you and mark that triangle off exactly 3 units, exactly up, straight up 4 units, exactly over 5 units, and try to connect it, you're going to find that it's not going to work. You're not going to be able to draw the triangle on a curved space and have it close up on itself like that, because it would be like taking this drawing and trying to bend it into a sphere. You're going to distort all of the distances and angles there. So the Pythagorean theorem for a 3, 4, 5 triangle like that is not going to work when you curve it. So when we talk about gravity around a black hole or gravity around a planet, the space and the time are curved in such a way that this Pythagorean theorem, and later on what we're going to talk about to be the distance formula, doesn't quite hold in the same way that it does here. That's how we measure the curvature of space, is what I'm trying to say. All right, enough talking about physics. Let's get back into the pure math. So this is what we call the Pythagorean theorem. Now we're going to draw a direct extension to what I know you probably heard of before, but we're going to go a little bit deeper. It's called the distance formula. Now, most people learn the distance formula and they just use it because it's not too hard to use, but they don't really know where it comes from. It turns out that the distance formula is exactly the same thing as the Pythagorean theorem. There is no difference. And when I say there's no difference, I mean literally there is no difference at all. If you already understand that this is true, then you already know that the distance formula has to be true. And so I want to show you that rather than just, telling you that and saying, believe me, I want you to understand that. So I want you to see that. So let's draw, in order for me to do this, I have to draw some kind of a coordinate system. So let's call X and let's call Y some kind of coordinate system. All right, so in this coordinate system, I'm going to have a couple of points. I want to find the distance between these 2 points. So this point is point number 1. I'm going to call this P, and it's going to be at coordinates x1, y1. Now, why am I labeling it x1 and y1? Well, because this point can be anywhere. I'm just putting it right there to illustrate it, but really the point can be anywhere because I can measure the distance between any points I want. I'm just drawing it here. I mean, the coordinate here is probably 3, 2 or 3, 1, but that doesn't matter. It's really at some x coordinate, x1, and y coordinate, y1. That's what that means. And I want to measure the distance between P. I want to measure it compared to another point Q, which has some coordinates x2, y2. So it's basically point x1, y1 and point x2, y2. Again, I've drawn this thing probably at like 10, 9 or something, but it doesn't matter. I'm keeping all the coordinates basically general because it can be anywhere. Now ultimately, I literally want to find the straight line distance, even though I can't draw a perfect straight line. I'm sorry about that. I guess I can try a little bit better. I want to find the straight line distance between these 2 points. That's probably not that much better, but you see if I got a straight edge out, I could draw a straight line between them and say how many centimeters is it between P and Q. Now there is a formula that we're going to learn, but I want to show you where the formula comes from. So what we're going to do is we're going to say, what are the actual coordinates? Let me switch colors here a little bit. What are the coordinates of this point P? Well, we already said it's x1, y1. Right? We said it was x1, y1. Let me just double check one thing real quick. Yeah. So if this is x1, y1, basically you can see this coordinate here is x1, and this coordinate here is y1. That's what it means to have coordinates x1 and y1, right? And then this coordinates of q here is x2, and the y coordinate of this point q over here is, I guess I gotta put this somewhere else, y2, right? So I'm going to put the y-axis label up above like this. So all I'm doing is showing you this is the coordinate of this point, this is the coordinate of this point in green, just like this. But if I really want to find the distance between them to make it all come into focus for you, what I really should draw is the fact that this forms a triangle. So this forms a base of a triangle here, and I'm going to draw this in blue. I'm not going to cover up the green to kind of draw it in parallel here. So you can see it kind of forms a right triangle. Notice this exactly looks like the right triangle we've drawn right here. You have a longest side called C. This is the distance between the points we care about, but there are also these other sides of the triangle, and there's a 90-degree angle here. So when you have any two points like this, it always has a 90-degree angle like this, and you can always form a triangle like this. And the distance between them is the distance that we want to actually calculate. The distance in this case is PQ. This is what we want to find, the distance between it, PQ. Well, if we learn from the Pythagorean theorem that the longest side squared is equal to the other two sides of the triangle squared and added together, then all we need to do is figure out what are the other sides of this triangle here. And we can see it, we can read it directly from the diagram. What is the distance of this side of this triangle? From here to here, what would it be? It's going to be the point x2 minus x1. Like if this were at 9 and this were at 3, it'd be 9 minus 3. That would be the difference in the coordinates, so that would be the distance here, right? And then this distance here is going to be what? It's going to be y2 minus y1, because that's the distance right here between these 2 points. So this is y2 minus y1, like this. So if you want to put numbers on it, if this point were 10 and this point were y is equal to 10 and y is equal to 2, it would be 10 minus 2, and you would have 8 units here. So if you want to find or use the Pythagorean theorem, c squared is a squared plus b squared, what we're going to do is we're going to say PQ, the distance here squared, is equal to this side here squared, x2 minus x1 squared, plus this distance here squared, y2 minus y1 quantity squared. Make sure you understand what I'm doing. This is the magic. This is the secret sauce of what I'm trying to show you. We're going to end up calculating and finding the distance formula, which you've probably already seen before, but I'm showing you that it comes exactly from the Pythagorean theorem. The longest side of this triangle is called PQ. We're saying that distance squared is equal to this side of the triangle, which is just x2 minus x1 squared, plus this side of the triangle, which is just y2 minus y1 squared. So this is a Pythagorean theorem. C squared is a squared plus b squared. That's all it is. Now to find the distance, of course, right now we have PQ squared, so what we have to do is take the square root of both sides. So all we'll have is the distance PQ is equal to, we have to take the square root of both sides. So we take the square root of this side, the square goes away. Here we have x2 minus x1 squared plus y2 minus y1 quantity squared. Now you may have remembered from algebra in the previous lessons that when you take the square root of both sides, you have to put a plus or minus in front of the radical. But what we have here is we're calculating distances. When you have a distance between 2 points in the plane, it's always going to be a positive number. The distance between me and you is always going to be a positive number. Even if I'm going a negative direction, the absolute value of the distance going in any direction is always positive. So even though you're always taught to put this plus minus here, because we're talking about distances, we never ever need the negative sign. So basically, it's always positive. So because of that, we don't even need to write the plus or minus at all. We just say the distance is the square root of all of this stuff that's under there. Now in your books, you're probably not going to see it written like that. You're going to see it written like this. It's going to be called the distance formula. And what it says is the distance d is x2 minus x1 squared plus y2 minus y1 squared, and then take a nice big fat square root around the whole entire thing. This is one of the most important things. This is probably the central concept in this lesson, the distance formula. So if you want to find the distance between a point here in the xy plane and a point way over there in the xy plane, all you do is you subtract the x coordinates of the points and square it, And then you subtract the y coordinates of the points and square it. You add those numbers together, and then the last thing you do is you take a square root. Again, most people just use it because it's not that hard to use, but they don't really know where it comes from. It comes from the fact that these things always form triangles, right triangles, and so it comes from the Pythagorean theorem. This distance formula is what we use to calculate the distance between points in space. When you get to more advanced science, like I told you about gravity, modern theories of gravity, we don't talk about just space, we talk about space and time. There's a very similar equation, not exact, but very close to this one, called it's called the distance formula in space-time. It's really called the space-time metric, really, but it measures the distance between points in space and time. And it looks really close to this. This big radical has quantity squared. It looks really similar to this. There's a slight change to it. I don't want to get into it right now. It has to do with how time works. But the bottom line is something that you think is kind of useless actually has far-reaching consequences. So we measure the distance between points in space-time. We measure the curvature of gravity by really using a very similar formula to this with space and time all mixed together. All right, so now what we want to do is we want to use this distance formula to calculate a couple of things in algebra here. We want to find, as an example, the distance between the points -1, 2 and the point 3, 4. So obviously I could draw this on a XY plane. I could plot them and I could draw the triangle. I could do all the same stuff I just did, but ultimately you don't need to do that anymore. Once you have the distance formula, there's no reason to plot it every time. You can just put the information directly into the distance formula knowing that it always works. So that distance formula is what? Again, it is x2 minus x1 squared plus y2 minus y1 quantity squared, and I'd have to take the square root of the whole thing. All right, so now we have to put the values in here. Now here's the thing. You have to subtract the values of x coordinate of one point and x coordinate of another point. So let's do it first one way and show you how it works. Let's take, this is an x coordinate and here's another x coordinate. So inside of here we'll say 3 minus, the minus sign comes from the distance formula, then you have a -1. So you have a double negative there because it's a minus the -1, but then you have to square that. And then you have to go the same way. If you go from this point subtracting this point, you have to go the y values in the same direction, 4 minus 2. Quantity squared. You can't mix up directions. If you go this way, subtracting, you have to go this way on the other point there as well. So then you have, over here, 3 minus a -1 is 3 plus 1, so you have 4 squared. And then over here, 4 minus 2 is 2 squared. And so you have the square root of all of that. So the distance between these points is 16 plus 4, which is the square root of 20. And so you have to ask yourself, what is the square root of 20? Well, I can do a factor tree here, right? I can do 10 times 2 and 5 times 2. So I can circle a pair here. So what I'm going to get is the distance. This 2 comes out of the radical, square root of 5. 2 square root of 5, and that's the final answer. So you say, what does 2 square root of 5 mean? Well, it means if I grab a sheet of paper and put XY tick marks on it, let's say I measure it in meters or centimeter, whatever the units you pick is what the unit of the answer is going to be. If I put the first coordinate at -1 centimeter and then up 2 centimeters, and I put this one at 3 centimeters and up 4 centimeters, then the distance, if I measured it with a ruler between those points, with literally putting a ruler between them, would be 2 times the square root of 5. Now you could put this in a calculator and get the decimal. You would get some value in decimal, but that would be in centimeters. If you put the original points in terms of meters, then the answer you get for the distance would be in meters. If the points were in terms of light years, then the answer you get would be light years. You see, it doesn't matter. Whatever units you use for the points is going to give you and dictate the units that you get in the answer between the 2 points. Now, one more important thing I want to point out is that it doesn't matter which point is x2 and which point is x1. In this case, I did 3 minus the -1. And then because of that, I did 4 minus the 2. But it doesn't matter which point is x1 and which point is x2, but you just have to be consistent. For instance, let's go the other direction. So let's say instead of calling this x2 and this x1, we'll flip it around and say this is x2 and this is x1. So we'll go the other way. We'll say -1 minus 3, subtracting this direction, squared. Then if we do it this direction, we have to be consistent. So we have to do 2 minus 4. quantity squared. I want you to make sure that you understand that this is exactly backwards from what we did here. The -3 minus the -1 is exactly backwards from -1 minus 3, and then the 4 minus 2 is exactly backwards of the 2 minus 4. But we're going to get the same answer because what do we have here? -1 minus 3 is -4 squared. 2 minus 4 is -2 squared. And you can see that the negatives, it's not going to matter because everything is squared inside. You're still going to have the 16, you're still going to have the 4, you're still going to have the square root of 20, and so you're still going to have 2 times the square root of 5. So the most important thing to realize for the distance formula is when you're calculating distances, it does not matter which direction you subtract, but you must be consistent. If you pick a point and say this minus this for x, then you must also pick the same direction for y when you're doing the subtraction. So, we've covered a lot so far. We've covered the Pythagorean theorem. We've shown you that when you draw these triangles on a flat board like this anyway, and it has a right 90-degree angle here, then the Pythagorean holds. C squared is a squared plus b squared. We showed you that the distance formula comes from the Pythagorean theorem. So this distance formula you get will hold for any points, again, in flat space. We're not talking about black holes or gravity or neutron stars. We're talking about on a chalkboard, on a sheet of paper. And we calculated the distance between 2 points, and we showed you that it doesn't matter the direction you do the subtraction. So we're going to do more problems, but that's the general idea. Now, the last thing we want to talk about is something called the midpoint formula. Some of you have been exposed to this and some of you haven't, but it's really, really simple to understand. What we want to do is, if we have 2 points like we did in the last part where we were finding the distance between them, let's say we don't care about the distance. We just want to figure out if we have 2 points in space, where is the point between them? Now, of course, I'm holding my fingers up, so you know the point is somewhere here in the middle between them. But what I mean by where is the point, I'm talking about if I give you the coordinates of 2 end points, and you can put your finger in the middle, cutting the thing in half, where is that point in terms of what are its coordinates? That's called the midpoint of the 2 original points you have. And so we have something called the midpoint formula. Now again, I don't want to just blab it out for you. I want you to understand where it comes from. So we have something called the midpoint formula. It's very easy to understand. It's actually easier to understand than any of the other guys here. So what we have here is, let's go ahead and again draw an xy plane. It's not going to be perfect, so this is x and this is y. And same kind of thing, I'm going to draw 2 random points here, P and Q. So we're going to call this again P. This is x1, y1, exactly the same before. And this thing we're going to call Q. It's going to be at some coordinates x2, y2. Right? Now I know that there's a straight line that connects these guys. I mean, I've drawn that. I know how to calculate that. That's covered with the distance formula, right? But I don't want to actually figure out the distance between them. Let's say I want to figure out where exactly is the midpoint of this line segment. It's probably somewhere right around there. It's hard for me to tell, but there's a point somewhere here that's exactly midway between the 2 endpoints. Like if this were 5 centimeters and this were 5 centimeters, and the whole thing will be 10 centimeters. It's right in the middle. I want to figure out what is the coordinates of this thing. Right? How do I figure that out? Well, first let's go take a look at point P. What are the coordinates of P? We already talked about this before. This is x1, and over here is y1, right? Now we have some coordinate point Q, and its coordinates are x2, and the y coordinates of this point is y sub 2. Nothing has changed from before. Everything is exactly the same. So my question to you is, how can I figure out what this point is in the middle in terms of its coordinates? How could I possibly figure that out? Well, this point has to have some kind of x value, and it has to have some kind of y value. And the way you figure out what the midpoint is you kind of forget about y for a second. You just look kind of, if you could just look down from above, then you would say the end point has some point along x here, and the end point has some point along x here. So midway between, this thing has to be equidistant from here to here and from here to here. So this point right here, the x value of it, has to be the average, x2 minus x1 over 2. In other words, the value of this x coordinate of the midpoint is the average of x2 and x1. In other words, I mean, if you think about it, if I have the endpoint, the x-coordinate of the endpoint is at 2, or let's make it easy. If the endpoint is at 0 and the other endpoint is at 10, I'm talking along the x-axis, then we know halfway is got to be at 5. So 10 plus 0 divided by 2 is 5. You're just averaging the 2 points. If you pick any 2 points you want, to find the middle of it, you take the average. That's what you do, right? So to find the middle in the x direction, you just average the x coordinates. And the exact same thing is going to happen over here. The y value here is going to be y2 minus y1 over 2. You just average the y values. So if I give you a point P and a point Q, you can always tell me the midpoint. The midpoint's going to have an average of the x values for the x coordinate and an average of the y values for the y coordinate. So the midpoint of the segment joining P located at x1, y1 and Q located at x2, y2 is, this is the way it's written in the textbook, and it's really confusing the way it's written a lot of times, but this is the way it's usually written. M represents the midpoint. The x-coordinate of that midpoint is x1 plus x2 over 2. That's the average of the x values. The y-coordinate is the average of the y values. Let's do it like this. y1 plus y2 over 2. You see, all this is saying, it looks really confusing, but all it's basically saying is the midpoint has an x value of the average of the x coordinates, and the y value has the average of the y coordinates. So it's going to be easier to show with an example, right? What is the midpoint between the segment defined by 4, -6 and -3, 2. Now, of course, I could plot 4, -6, and I could plot -3, 2, and I could put my finger in the middle and say, aha, it's about right there, and do all that. But I don't need to do that. I mean, I have the midpoint formula. I know what it says. And so the way to do this is you say, okay, the x value of the midpoint is just going to be the average of these x values here. So it's going to be 4 plus the -3 over 2. 4 minus 3 is going to give you 1, and then you're going to have a 2. So the x value of the midpoint there is just at a location of 1/2. And then you're going to have the y value of the midpoint, which is again the average of these guys here, -6 plus 2, -6 plus 2 over 2. That's how you average things, right? So you're going to get on top, you're going to get a -4 over 2, and then you're going to get a -2 for this. So what you would write down for your final answer is the midpoint exactly between these two, the line segment joining these 2 points is going to have an x-coordinate of 1/2 and a y-coordinate of -2. And I promise you, if you get some graph paper out and you plot this point, and you plot this point, and you look at this point, it's going to be right in the middle of the segment, just like this. All right, so that was a long lesson. I had to kind of cover it all together because in the next few lessons, we're going to have topics that kind of jumble all of these concepts together. So you have to know what each of them all is, and so we can do some more complicated problems. Pythagorean theorem is something that is not proven. It is something that is just observed. Anytime you draw a triangle with a right 90-degree angle in one corner, then you always know that this relation holds. If you label the longest side C and the other 2 sides doesn't really matter, then this equality holds. Again, I showed you that in curved space, I mean, I didn't really show you, but I'm telling you that in curved space, this relationship doesn't hold, right? The angles inside the triangle also get distorted and look weird as well. And then when we look at a distance formula, you can see it comes directly from the Pythagorean theorem. We did problems to calculate the distance between points. We talked about it doesn't matter which direction you do the subtraction as long as you're consistent. When you pick one direction, you have to pick the same direction for the y value. And then we talked about the concept of midpoint between 2 points and the fact that it's just an average of the x coordinates and the y coordinates. So I want you to make sure you understand these concepts. Follow me on to the next lesson. We're going to do some more complicated problems dealing with the Pythagorean theorem, the midpoint formula, and the distance formula.